to the sixth day session of the AICT ATAL sponsored faculty development program on smart energy systems for climate resilient and sustainable development. Over the past 5 days, this FDP has been a wonderful journey of knowledge and sharing. And today, as we step into the concluding session, we are honored to have with us Dr. R. Shivakumar, Dean, Sponsored Research and Industrial Consultancy of VIT Chennai, who will be delivering an insightful session on application of CSD in energy storage techniques. Welcome you, sir. Now, I request Dr. Lakshmibai ma'am, co-coordinator, to introduce Dr. R. Shivakumar, sir. Over to you, ma'am.
Thank you, Dr. Anisha. Good afternoon, everyone. On behalf of SCSVMV Kanjipuram, it gives me immense pleasure to warmly welcome you all to today's session of our one-week faculty development program on smart energy systems for climate resilient and sustainable development. We are deeply honored to have with us Dr. Shivakumar R., Dean, Sponsored Research and Industrial Consultancy, VIT, Chennai, to deliver today's lecture on applications of computational fluid dynamics in energy storage techniques. As we all know, energy storage plays a critical role in the effective utilization of renewable energy systems. Computational fluid dynamics has emerged as a transformative tool that enables us to visualize, optimize, and enhance the safety and efficiency of energy storage technologies, be it thermal, electrochemical, or mechanical, or hydrogen based system. With his rich expertise in research and industrial consultancy, Dr. Shivakumar will guide us through how CFD helps address the challenges of efficiency, safety, scalability, and cost in energy storage, while also pointing to emerging opportunities such as digital twins and AI integration. We are indeed privileged to have him with us today, and I am certain that his section will be both insightful and inspiring. With great pleasure, let us now invite Dr. Shivakumar R to begin his session. The session is yours. Please, sir.
Thank you, ma'am. Thanks for the introduction. The screen visible?
Yes, sir. Yes, sir.
Yes, sir.
Okay, thank you. Right. So the topic is given to me is the application of CFD in energy storage techniques. So this is based on my experience in CFD. I'm sharing this this 1 hour content. So previously I was worked in Infotech Bangalore and G Bangalore as a lead engineer in CFD. I worked on mainly on the gas turbine combustion, and then even in here VIT Chennai, my work is mainly focused on CFD. So CFD is a very good tool to replace the experimental, but we can't say replacement. It is a complementary tool. So with that, we can reduce or minimize the number of experimentation. So that is a benefit of CFD. So that's the reason wherever flow is there in industry, they're using this CFD as a substitute for experiment. So with this, I will start this. So if it is interactive, to be nice. So if you have any question in between, you can ask. You can stop me anytime, and you can ask question. So why CFD in energy storage? As Lakshmi ma'am pointed out, these are the main reasons why CFD used in energy storage. So mainly the energy storage systems involves a lot of complexity in interaction of heat, mass as well as fluid flow. So to get into it up, so CFD helps in terms of visualizing and quantifying these phenomena. Okay, and also it helps in optimizing the design of the system, as well as it will help to improve the efficiency and also safety point of view. And we can say this CFD actually virtual type of things because we can instead of doing experiments, we can make it up as a virtual prototype, and we can do n number of experiments to reduce the cost. N number of simulations, we can say n number of simulation to reduce the cost of experiments. Sometimes even impossible things can also be done using CFD, and we can say that this will not work out. So, but in experiment that we cannot do that. Mainly on the when you go for larger systems and where safety involved. For example, if a fire happen in a building, okay, so what will happen? What is the impact of this fire to the building? Whether it is safer to escape out. So all these things, if you want to do a practical experiments, you are wasting a lot of money in identifying the root cause, and then what are the things happening there. But if you do the simulation with a minimum cost, we can able to predict this is the thing going to happen when the fire hazard occurs. Okay, that is the way it helps in reducing the cost of experiments. So, if in a nutshell, we say that it is a very good tool. It's that's why it's specifically mentioned as it's a virtual tool. Okay, it helps to reduce the cost. Okay. So, what are the domains of energy storage where we can use CFD? So, listed here a few things. One is the thermal energy storage, which can simply called as TES. Another one is the electrochemical energy storage. Third is the mechanical energy storage, and fourth one is the hybrid and hydrogen storage. And also we can say advanced storage systems all come under this fourth category. So if you say thermal energy storage, so the heat, sensible heat, okay, that can be used as for this, where it's molten salt and water tanks, they will use it up. And latent heat means phase change materials. So I'm going to explain about this in a case study. So I put at the end case study about this latent heat used in battery management system. And then thermochemical, it may be endothermic reaction or exothermic reactions. And what is the role of CFD here means it is used to find out the heat transfer happening inside the system, as well as how the natural convection helps in analyzing the flow. Okay, and second one is the phase change front, tracking in phase change material. And third important thing is design optimization. Tank geometry optimization can be done for getting the uniform temperature distribution. So this is about the thermal energy storage. And in terms of electrochemical energy storage, mainly we can say battery. It may be a lithium-ion battery or any other battery, aluminum air battery, and a lot of batteries. Okay, where one of these energy storage device. So here, what is the role of CFD means? We can do some coupled analysis, electrochemical thermal modeling, and also we can do some how the flow is happening inside the electrolyte flow happening inside the battery. That we can analyze. And also thermal runaway simulation, it means when the fire happens, what is happening. And also the cooling system design. Okay, so that's why I put as like the case study, I use this battery, it will be because lithium-ion battery is used everywhere. So I took this as a case study, and thermal management of lithium-ion battery, I'm going to explain at the end. And the third important is the mechanical energy storage. Okay. So here we can say compressed air energy storage. That is the main thing. Another one is a pumped hydro storage. Also, you can say that in flywheels, if you see in vehicles, and the engine flywheel will be there. That flywheel absorbs this energy and then releases whenever required. And here we can say CFD role is the airflow, turbulence, and thermal losses can be studied, and also the interaction, the turbine pump systems. Okay, that flow, how the flow happens, that dynamics can be studied here. And also, if you want to do the aerodynamics drag and the flywheel coolings can be studied using this CFD. And the last one in this category is hydrogen and hybrid storage. Nowadays, hydrogen is going to be replacement for our two-wheeler or four-wheeler, because they're going for alternate energy. So the challenge is the hydrogen tank. So people are working on it up. So, and also metal hydrides. Then the other one important thing is the supercapacitors. Okay, so replacement for batteries, they are thinking of supercapacitors. So here the CFD helps in finding out the hydrogen boil off and pressure relief, and also the how the heat and mass transport happen in porous hydrides, that is CFD plays a role, and also to do the multiphysics analysis for coupled thermal performance can be done using CFD. So these are the 4 domains are used. So if you take it up, first one is thermal energy storage, second is electrochemical energy storage, and third one is the mechanical energy storage, and last one is the hydrogen hybrid, I can say allied storage or advanced storage systems. Any doubt up to this? Anything you want to add?
No, sir, you can proceed, sir.
Okay, thank you. Right. So what are the benefits of CFD in energy storage? So if you take it up, these are the main important points. So design optimization, that is geometry we can optimize, and also materials can be optimized. Okay, the phase change material, the ratio of mixing can be analyzed using this CFD, and also thermal management can be enhanced. Okay, by suitable cooling arrangement can be put it up and enhance the thermal management, and efficiency can be improved, and also the lifespan of a storage device can be improved by putting proper cooling systems and the materials. And also increase safety by predicting failure modes. There is also another point you can say, increase safety by predicting failure modes. Okay, so what are the challenges there in energy storage? Okay, it's not only CFD, general in energy storage, what are the challenges? If you take it up, these are the 4 main challenges. One is the efficiency, second is the safety, third one is the cost, and last one is the scalability. Okay, so efficiency plays a major role because even a 1 or 2% increase in efficiency will reduce the cost. So CFD modeling, if you do accurate CFD modeling, it's very difficult. But if you do this accurate modeling of heat transfer, fluid flow, and electrochemical reaction, the problem is the CFD modeling, when you go accurate, the mesh count, I'll come into this detail in later. So the mesh count will be increased and a lot of equations to be solved. When it is doing that, we need high power computing, so it may be computationally intensive. Okay, and the losses, what are the losses happen because of the hotspot? Loss mainly due to hotspots, and hotspots means some places it will be very hot, another place it will be not much, that much. One place it will be concentrated. So because of that, the material will lose the strength, and it may be broke also. And then non-uniform flow distribution, the flow will not go uniform. Okay, some problem with the geometry or the arrangement what we have done inside. Okay, some obstacle or something will be there, some protrusion. So this will affect the flow, and also the parasitic reactions here, which reduce the efficiency, round trip efficiency to overall efficiency, it will reduce. And the third is balancing high energy density with minimum energy loss. That is also a very challenging one. So these are the problem because of the efficiency is very low. And second is the safety. So when come to the safety, we mainly in the battery, it is called the thermal runaway. Okay, so predicting and preventing it's very difficult. Some of the cells may be damaged because of that cell damage. The fire it will give a fire hazard. Okay, and also we have to solve the multiphysics problems. Okay, it involves a lot of interactions that is in between thermal, electrical, and then chemical reactions. So to capture this, we need a very good simulation techniques. Okay, that's where CFD plays a role. And flammable electrolytes. Okay, that is also a problem if you take a hydrogen storage devices and high pressure storage, for example, hydrogen. These are all giving a safety problem. So this is second problem challenge in energy storage. And third one is the cost. So when you say cost, okay, even we are saying simulations reduce the cost, but because of the high computational resources required, so the cost of CFD simulation will become huge. Okay. And also when you do the experimental, it become very expensive by giving the prototype and also doing the validation study. So it result in a lot of money. And also material cost. Okay, material cost become higher. So we want to reduce the material cost. Okay, become, for example, rare metal materials, batteries, and composites if you use storage tank. So this one, if you do, then maybe reduce the material cost. So so durability, because of the when you play with the material, the durability will become also problem. Okay, so if you go with the material with not standing these stability, then the durability can be the issue. So because of that, we have to make some compromise in increasing the cost by putting a proper quality material. Okay, and last challenge is the scalability. See, if you see, most of the times we do the experiments are the experiments in lab scale. Okay, and sometimes whatever we are doing in lab scale, it is difficult to scale up in a real model. So fail to replicate behavior at industrial scale. That is a big problem. Okay, so if you, for example, if you take a ship, it's a bigger one. The bigger ship can't be tested in lab. So we have to scale down the model and using a smaller pond to test it up. So that will give you, sometimes it will create a problem. So the realistic future will not be captured. So there is a problem in using this models at the validation in this lab. And CFD scaling challenges, that is also important because turbulent, it's a random behavior. So what will happen is if you consider with a small scale model, whatever the features you are putting it up, turbulent model is using, it may not be valid when you go for a bigger model, bigger domains. So there is a problem, and also the mixing flow maldistribution. I already explained about it, and thermal gradient. There is a shock waves or something happen. So sudden change in temperatures. So these and all will be the issue when you use the scaling when you do the scaling in case of a CFD. And the third is the important point, we can say integration with renewable energy grids. Okay, so for that we need robust and large scale storage systems. Okay, but it is not still available. So people are still working on it up to improve to optimize it up. So these are the challenges we can say by using for the energy storage. So one is the efficiency, another one is the safety, and third one is the cost, and last one is the scalability. Okay, so how the CFD helps in overcoming these energy storage losses? Okay, we are saying that by using CFD, multi-physics involved, the cost is more. Okay, but how it will overcome? Okay, so some of the points, the same thing, we put it up in how to improve the efficiency using CFD, how to enhance the CFD, and reducing the cost. And last point is the enabling scalability. Okay, these challenges to overcome this. So these are the four same points we'll consider. So how to improve the efficiency means now some of the design changes we have to do and optimize it up. That is why we are saying battery and all flow channels. Okay, and optimize it up, and fuel cells, batteries and fuel cells, where to optimize the flow channels to get a uniform reactant distribution. So for that, CFD will help you, and also to predict thermal behavior to reduce the hot spot and energy losses. Okay, that is an important thing. Okay, so based on that, we can correct our system, and also increase the efficiency by virtual design iterations. It means we are running the cases with the different different models, and then we parametric study we can do, and then after that we can do the prototyping so that the efficiency can be improved. And enhancing safety. Okay, so when you say enhancing safety means we can simulate the thermal runaway scenarios. Okay, to design effective cooling strategies, which is realistically, experimentally, it is not possible. It's very costly. And also, we can model some fluid leakages, gas evaluation, and pressure buildup in real time. Okay, so that already I told you that if you do the real time, it will be costly. So I put in model itself, I'll provide this option of fluid leakage, and then pressure buildup. I make it in such a way that these things simulation able to tell what's the big how it will behave. The system will behave for this leakage and all. And also the guide the development of safer material and containment system. So that's how the CFD helps in enhancing the safety. And cost wise, how to reduce it up using CFD means that's why the CFD by using a lot of by doing a lot of simulations, we can reduce the number of experiments. That's why already I told you CFD is not replacing experiment; it reduce the cost of experimentation. Okay, so some of the things, even if you do the experiment, we need to do it up for 6 months, and then only the experiment can be done. But with the CFD now, with the available supercomputers and all, it can be done maximum of 1 month. We can get the result, and we can able to get some conclusion whether we can do for this experiment is okay or not. So that type of things we do, then the cost can be reduced. And then by using a lot of configurations, we can test that we call as virtual testing. Thereby, the cost can be reduced. And then optimal material usage, so we can put proper electrolyte thickness, and then use different types of fluid and test which fluid will be optimal for this so for this design, everything we can do. Thereby we can say that by using this type of material, fluids, cooling fluids, materials, and electrolyte thickness, we can bring down the cost. Like that we can argue, and we can change in the main in the actual model. So that's how the CFD can help you. Okay, and the scalability. So scale up is if you take it up in battery thing. So cell we can create, and then module. Then from there we can go with the pack, and finally grid storage. So by all these things, CFD will help you to design and finalize the things, and we can model large scale systems for flow uniformity and thermal management. So for example, I showed about the ship. So bigger ships can be modeled using CFD, and real time things we can predict it up. So that's the way it help and also support integration with renewable energy grids through predictive load balancing. So by we can able to identify the load balancing. So by using CFD, thereby the integration of these renewable energy grids can be possible. So this is how the CFD helps in overcoming the what are the challenges in energy. Okay. Okay. So now whatever preview I given is related to the energy storage domains, and then the benefits of CFD, and what are the challenges the energy storage is facing it up, and then how the CFD helps in overcome these type of challenges. So now I talked about CFD, but so what is CFD and how it helps? That I am going to tell in a couple of slides. So till now, anything you want to add, or anything I missed out? Please.
No, sir, you can proceed, sir.
No, sir, we can proceed. Okay, right, ma'am. Coming to the fundamentals of CFD. So what is CFD? CFD is computational fluid dynamics. Okay. So it's predominantly used by mechanical engineers, electrical and aeronautical engineers. Okay, nowadays the electronics engineers and the computer science engineers also started using it up. Okay, it will be very useful in wherever flow is happening. Okay, so we can able to correct it up, and thereby the experiment can be properly done and system can be corrected up. Proper system can be used. So this computational fluid is nothing but it's analysis of a system which involves fluid flow, heat transfer, and also some other associated phenomena like combustion. So by solving these things by using mathematical modeling, we can say by solving the partial differential equation and using numerical methods, say discretization techniques and different solution techniques, and also using the softwares. So the softwares, we can say it's a preprocessor, solver, and a post-processing operators. Okay, so already we said virtual prototyping, we said previously. If you see that left-hand side, the geometry shows the real experiment, picture shows the real experiment, whereas the right-hand side is CFD information. If you see both, almost it's similar. So that's why people are calling CFD as a CFD as the virtual flow laboratory. Okay. So how it is possible, this virtual flow laboratory, how it can CFD is possible nowadays is it's because of high performance computing. So CFD we can use wherever possible. Okay, in previous days, if you start for the history of CFD, if you take it up, for solving one case, they used a lot of parallel computing, and then they used 6 months to get simple result. But nowadays, with the supercomputers, and a lot of the currently available the workstations, we can reduce the time available to solve it up. Okay, now I have done in my PhD, I used CFD. So it almost 2005. So when I used, I took for doing one simulation, it's 1 month using LES, large area simulation, we call it large area simulation. But the same thing nowadays, we can do it up in 2 days time. So that type of computing facility is available nowadays. Okay, if you, that's why people are going for this high performance computing and able to get the result quicker, so that the time can be optimized. Okay, that's why people are started using CFD. Okay, so how it can be modeled? What are the methods available? Means we have a discretization methods. We call as a we also call as a modeling method. There are mainly 3 methods people are using it up: finite difference, finite volume, and finite element method. Okay, so if mostly the people previously used is a finite difference method when they do the programming manually. But nowadays in all our computer-based simulation, so people are using finite volume method. Finite difference using differential equations, whereas in finite volume method it uses the integral equations. And the third one is the finite element method. Usually this is for solid analysis, but structural analysis, we can say structural analysis. But some of the softwares can be used for doing this simulation packages. Using this finite element method can also be used to solve the CFD. That's why finite element method also one of the method we put it under the discretization techniques. So the finite volume difference, if you take it up, it is the one of the oldest method. Okay, and also the easiest method for simple geometry. That's why people start using when they solve for a smaller simple geometry. And here the equations are in differential form. It should be converted into different expression. Okay, so we already informed it is used only for simple geometry, not for complex flow. So this is how the discretization happens. If you take dt by dx, it will be Ta minus by delta x, difference between the temperature and adjacent nodes divided by the distance between the nodes. If you say here, this is the I minus 1 I and I plus 1. The distance between the node is delta x. So based on that, we are writing this equation as Ta minus 1 by delta x. This is called the discretization equation. And second is the finite volume method. So here the conservation equation, whatever we are going to use, are integral form. And here the domain is given to subdomains. That is subdomains. That is we call as a number of control volumes, small control volumes. And for each control volume, we apply this conservation equation, and the equations are solved for it up. It is good for both simple and complex geometries. If you take it up in CFD simulation packages like Fluent, CFX, and TaskFlow, these packages use this finite volume method technique. Okay. So here this one, each one we call as a control volume, and the centroid is at the center of this control volume. And these are like interior nodes one to this inside the nodes. Whereas this dark color rounds, these are circles are called as a boundary nodes because it is at the boundaries. So I already informed that informed you that the finite difference and finite volume methods are used for a flow analysis, that is CFD. But FEM also used, but FEM was initially developed for structural analysis. But here the large structure, similar to this large structure, divided into small element, and characters of each element return matrix contribution. So by combining all these contributions, we get a matrix equation that can be for a whole geometry that can be solved to get the final answer. Okay, so these ANSYS and Abacus packages are using the finite difference method, finite element method. And how we get the answer in CFD means we are solving the equations. So that equations, the major equations which we solve is called as a governing equations. Without that, CFD run is not possible. So one is the also we can call as this is a mathematical statement of conservation law of physics. Okay, so there are three laws. One is the mass of fluid is conserved. Okay, so from this we'll get the equation as a continuity equation. And the second law is the Newton's second law, rate of change of momentum equal to the sum of forces on a fluid particle. This we called as a momentum equation. And the third one is the energy equation. Here it's based on the first law of thermodynamics, where the rate of change of energy is equal to the sum of rate of heat addition and the rate of work done on a fluid particle. Okay, so these are the equations are current equation, momentum equation, and energy equation. The conservation law, whatever we are using is, one is the fluid, mass of fluid is conserved. Second one is the Newton's second law of motion, and third one is the first law of thermodynamics. So based on these three equations only, the CFD model works. Okay. In addition to that, we will solve some additional equations. Okay, it may be turbulence modeling, or it may be a combustion, or it may be multiphysics. Okay, so all these things we have to use additional equation. But the basic equations, whenever required to solve CFD problems, is these three only: continuity, momentum, and energy equations. So this is the governing equation for incompressible fluid flow. Okay. So current equation is written like this: dou I by dou x plus dou I by dou y plus dou w is equal to 0. I'm not going to explain this. Okay. So just for the clarity, I put it up. So these are the momentum equation. It's a three momentum equation: x momentum, y momentum, z momentum. These are the momentum three directions. The momentum equation is. And last one is the energy balance equation. So this is the energy balance equation. This for incompressible flow where the density is constant. Okay. So that's why it's written like this. And whereas this is a compressible flow, this is the current equation, and these three are momentum equation, and these are some of the terms, shear stress and normal stress terms used in this equation, this tau xx, xx. And final one is the energy equations. So here the density will vary with temperature. Okay, so there is a thing in case of a compressible flow. Okay. So how this simulation happens? So we already I already told about this the discretization techniques, and I talked about what is CFD and then what is discretization techniques. Okay, now so we'll and then also the equations, whatever equation to governing equations to be solved. Now we'll come to this thing how the CFD simulation happens. Okay, we are saying CFD simulation and all. What are the steps involved in CFD simulations? So if you take it up to the CFD simulations, there are three major steps we can say. One is the pre-processing, second one is the solving, and third one is the post-processing. Okay, so in pre-processing, it involves the geometry creation, then mesh generation, setting up boundary conditions. So these are the major steps involved in pre-processing. And solving means the governing equations or whatever is there, that equations to be solved by using proper numerical methods. And last one is once the equation is the flow is solved and converged, then we have to use the post-processing techniques to analyze the result. So these are the three major steps involved in CFD simulation process. Okay. So if you take it up, what are the different similar packages available means, if I can say ANSYS Fluent, ANSYS CFX, these are all owned by ANSYS, and another one is OpenFOAM. It's a free software, open software, and also COMSOL Multiphysics. It's a paid software. So with this software, we can do the different analysis, each one having own many merits. If you take Fluent, it's very good in combustion and then compressor analysis. Then if you take a CFX, it is good in turbo machineries. And COMSOL multiphysics calculations, okay, wherever it happens, then there it will be very useful. OpenFOAM is without any the background, okay, using the coding. If you write the manual coding, then I can go with the OpenFOAM method. Okay. So this is the detailed flow process, CFD flow process. So if you take it up, it will be the first three, geometry, physics, and mesh represent the pre-processing. Second one is the solving. And the third one is these two parts are called as a post-processing. So if you take it up geometry, it involves the selecting the geometry, and then some parameters we have to set it up for geometry, and how the shape will look like, size will look like, that and all we will decide in geometry. And physics means whether any temperature is involved or heat transfer is involved, then we have to use where we have to switch on heat transfer or not, and whether flow is compressible or incompressible. What are the different fluid properties, flow properties? For example, I am using a material called air flow material. Then what are the properties I have to use, or I have to use water? What are the properties I have to use? Like that, I have to decide. And then which type of turbulence model can be used? That is called viscous model. And the boundary conditions we have to set. And last one is when you solve for this, we have to set with the initial condition, then only the problem can be solved, because in numerical methods, to solve this any equations, we need some initial values. Okay. And the meshing, there are different types of meshing, unstructured and structured mesh. We are going to discuss in detail now. And solving whether we have to stay, whether it is a flow is steady or flow is varying with the time. Okay. And then how many time iterations we have to use, and what is the time scale, or if it is a time study. And third one is the convergence limits, and then precision and numerical methods, numerical scheme, what type of numerical schemes we have to use. Okay, and in terms of reports, the post processing, we are using different report things. One is called reports, and the second one is the flow visualization techniques. So in the flow visualization techniques, so we use contour plots, vector plots, and then streamlines, grid plots, and so on. Whereas in the reports, we can give the numerical values. Okay, because see, whatever we use in visualization, it's a qualitative, it's not a quantitative. So by using the reports, we can get the quantitative values. That's why people are using this one, which the report tools to get the values. Okay, just a second. Right. Okay. So after that, are you able to grab something?
Yes, sir. Yes, sir.
Yes, sir.
What
Only
only
little bit,
one
only little.
one small doubt.
Yes, ma'am.
That is, CFD is often computationally intensive.
Yes,
So
ma'am.
especially when modeling complex interactions like heat transfer, fluid flow, chemical reactions in
Yes.
energy storage systems, high
Yes.
fidelity models can give accurate insights, but
Yes, ma'am.
they demand significant computational resource like time. And
Yes, ma'am.
while simplified models may reduce accuracy but are more practical
Yeah.
while design iteration. In
Yes,
your
ma'am.
experience, how do you approach this trade-off between simulation accuracy and computational cost? And
Yeah.
what strategies or tools do you recommend to achieve an optimal balance in real-world system?
Yes, ma'am.
Uh,
This is a good question, ma'am. So one is the two ways we approach. One, whether I need the accurate result, or I want only the trend, whatever we're going to get with experimental. So based on, and also the time availability. So the customer is asking for result tomorrow, then I can't go with high competition intensity. I can't use it up, because if you use it up, it will take some more times, and if it fails also, I can't rectify within a day. So at that time, so I'll go with only the simplified model, so that I'll get give a customer feel that okay, this model will predict, and we are able to get the whatever the experimental results we are going to achieve. That trend we can able to tell them, and if he is satisfied, then he will give some more time, because we usually we call as a different parametric study. So parametric study we used to do with simple the the intensive model. And once the customer, whatever the requirements fulfilled with the customer, then what we do is we will go with one or two simulations with higher correct model. Okay, and using the meshing will be very fine, So the mesh count will be more, and also the computational techniques, whatever the turbulence model, whatever you're using, will be high accurate model. So by using that type of techniques, we can reduce the, we can able to get a final result that customer is okay, then he will go for an experimental. That is the way we use it up. Now, now the people are started using AI. So when you use AI, if you do 2 or 3 computation analysis, so with that, they can able to find out the trend using the AI, and they can predict the future, how this can be for a different type of flow parameters, how the flow behaves inside the system can be studied. That's why the AI and the digital twin models, whatever I put up in the last slides. So that things will talk about these things. Okay. This is how we usually do. Mainly the model, whatever we are choosing in the called turbulence modeling, that is the main factor. In turbulence modeling, if you go with the 2 equation model, we call K epsilon and K omega models, then the time taken will be less. So that's why in industry it is called as a workhorse of engineering problems. Okay, that way we use it up. But if you go with the larger simulations, this type of things, the complexity involved is more and time taken will be more. So that will be used only when customer request. Otherwise, we will not use it. Yeah. Yes, ma'am.
Thank you, sir. Thank you, sir.
Okay. Okay. Right. So the here whatever we talked about the geometry selection and then the meshing, that is the main part, and then we have to select the physics involved. So if we go with the geometry, I'll take into a small simple geometry. For example, if the flow is happening inside a pipe. Okay, so this is my the pipe. Okay, the flow is going like this and then coming out like this. Okay, so how this can be solved? Okay, using CFD. So this model is a geometry. We simply call as a geometry. It's a pipe without any thickness. We are not bothered about thickness. We consider how the flow behaves inside. The flow is, for example, I want to predict the flow behavior, whether it is laminar flow or turbulent flow, and how it behaves like that. We can use it up. So this is a velocity profile for laminar flow, and this is for turbulent flow. So I want to find out this. So how to model it up? Okay. So what will happen? This geometry, for example, the pipe length is almost 1 meter. If you take it up, and this diameter is somewhat 0.25 meter. Okay. Then what will happen is, so I am going to model this like this. So this entire, so when even water is coming in, and I say water is coming here. Okay. So when you say water is coming here, it means it should be open. But in CFD, we can't open it up. We have to close the domain. Okay. This then only we can give the boundary conditions. The whatever water is coming at what velocity, like that we have to give. So for that we need some surface. So for that the boundary is closed. So this closed domain, one closed domain, this closed domain is called as a computational domain. So there only we are going to do our analysis. So the geometry is different, computational domain is different. So geometry can be anything, okay? But whatever the thing we are going to use it up for doing the analysis, that is called as a computation domain. So this is my computation domain. So this computation domain, I am going to solve the equations in this computational domain. So when you solve these equations, I can't directly solve, okay, with the flow and say that the flow comes here and flow comes here. The equation I put it up. So what I have to do is I have to divide this entire domain into smaller subdomain. Okay, that subdomains, this type of subdomains, that's see whatever here it is mentioned here. This type of subdomains is called as either cell or a control volume or a grid or elements. Okay, so based on sometimes if you're using a finite volume method, people are called as a control volume. And if you use a finite difference, people may call as a grid. Okay. And if you use a finite element method, then people will call as an element. So this dividing the domain into subdomains, we called as a we called as a grid or a mesh or a control volume or a element. So with that only the problem can be solved. Otherwise, the problem will not be solved. That's why the computationally more expensive. When we say computationally more expensive means this domain, whatever we are doing it up, each cell, this is a cell. I can reduce the cell size. It's called as a fine mesh. Okay, I can reduce the size, and thereby the number of mesh count can be increased. For example, 10 lakhs or 20 lakhs, like that, I can create a cell. So if I use a 1 lakh cell, then when you compare these two, 10 lakh and 1 lakh, so this 1 lakh will be computationally less expensive, and 10 lakh cell will be computationally more expensive, because for each cell we have to solve the equation. So 10 lakhs if you solve, so it means 10 lakhs times the equation will be solved. Whereas here it's 1 lakh time will be solved. So for each iteration. So the time taken will be less for 1 lakh when compared to 10 lakh cells. So that is the reason it's computationally we call as expensive, based on the number of the cells involved. And another one is how the equations. So if I use two equations to solve this problem, then easily I can iterate. But if it is 8 equation model or a 7 equation model, then what will happen? The time taken will be more to solve the equations. So this is how the problems we are saying is computational expensive, or it's highly intensive, like that. Okay, so this type of domains is important, subdomain is important. So here we call as a fine mesh or a coarse mesh. That's how we'll come to this later. So these are the different types of the grid pipe we are using it up. If it is a 3D model, we use tetrahedral, hybrid, or prism, or hexahedral. Mostly people use hexahedral and tetrahedral. Prism will be combined with tetra. Pyramid we will try to avoid. Okay, industry people will not prefer pyramid. And in 2D models, we'll use we'll use a triangle and quadrilateral. So these two are, sorry. So these two are for a 2D geometry, and these cells are these cells are for a 3D model. And this one we'll try to avoid. People use hexa, tetra, and prism model. Okay, now people are started using polyhedra. This is also one of the polyhedra cells. Okay, so it will reduce the number of mesh counts. For example, if it is tetrahedral cell 10 million, so this can be brought down to 3 or 4 million using polyhedra cell. So that's the advantage using polyhedra. So now a lot of the meshing software, the analyzing software supports the polyhedral mesh. So we can directly create the polyhedral mesh and you can use it up, or we can create the tetrahedral and convert this into polyhedral. That is also possible. So this is about the selection of grid type and type of cell. So this is a different type of cells we have. Okay, we call it as a structured. We call it as a structured grid. Okay, this is structured grid. Another one is unstructured grid. So structured grid, if you see here, every cell have a uniform sizing. So that is also one of the reason we can say. And the other reason we can say is each grid point, if you say how many cells are adjacent to it. So in this case, if you see 1, 2, 3, 4, 5, and 6 cells are here. Okay, this node is adjacent to 6 cells. Whereas this node, the adjacent cells 1, 2, 3, 4, and 5. Okay, this is 5. And here and all we will see here this node we have only 4. Okay, so here, but whereas here it is everywhere it is a uniform. Here everything everywhere if you take it up, each node is shared by 4 adjacent nodes. Okay, but in unstructured grid it is not like that. It may be 4, 5, 6, or 7 or something. So here it is not a uniform. That's why people will call as a structured grid and unstructured grid. Another one is block. For each block we can go with separate structure. That's why it's put like this, block structured grid. Okay, and which type of meshing I have to use? Okay, when you mark the model. Okay, if you have a simple geometries, then if it is a simple geometries, people started using this model quad. If it is 2D, we'll use a quad, and if it is 3D, we'll use a hexa machine. Whereas complex geometries, we have to use 2D for tri for triangular cells for 2D, and tetra for a 3D model. Okay, so here you can see here it's a simple step flow, step pipe. So it's simple model. So we used hexa element. We use this hexa element. Whereas this flow around the aeroplane and flow around the tank, it's a bigger model and very difficult to meshing because a lot of complicated parts are involved. So we are using a tetra mesh for it. Okay, so this is how the people will select the mesh, which mesh we have to use. There is hexa mesh and tetra mesh. Previously in industry only hexa mesh they will consider, but nowadays they allow tetra mesh also because of the time limitations. So we don't want to do that hexa mesh. And tetra mesh is very easy to create and quick to solve. So that's why industry people prefer to go with tetra meshing with the prism. Okay, and nowadays we are using polyhedra also. So this is a grid generation. Now, if you see here, see this type of thing. This is a flow around a cylinder. Okay, this is a flow around a cylinder. If you see the flow around a cylinder, what will happen? The flow comes here and divert like this and go. Then it will form a recirculation here. Okay, it will come like this, and then once circulated, it will go off. So to capture this physics, the flow behind the cylinder, okay, I want to capture this physics. So capturing physics. So what I need is I need a fine mesh near it up. Okay, what is my fine mesh and a coarse mesh? So if you have a geometry like this, I have the mesh like this. This is called a coarse mesh. Okay, in the same model, if I divide this into smaller subdomain, okay, then this mesh is fine mesh when compared to this mesh. So there is based on the comparison only we can able to say it's a fine mesh or a coarse mesh. Okay, this is also fine mesh. Now, if you put a very small mesh count here, then this can be a fine mesh when compared to this cells. Okay, so we have to decide which feature I want to capture. Based on that, I have to put a fine mesh near or a coarse mesh I have to put. So this place. So this place, I want to capture the physics. So here I have to put a fine mesh, and the remaining places here I don't want to capture a physics. Then I can put a coarse mesh here. So that's why it is written wherever we need to capture the flow physics. For example, in this bottom case, this flow around this V cutter. So when a flow comes here and then it will divert, it will recirculate and then go off. Okay, burning happen here, combustion happen here, and then go off. So to capture this flow physics, we have to go with the grid. Which type of grid? Fine mesh or coarse mesh I have to put. So mainly when you capture the boundary layer, I want to capture the boundary layer. Then only boundary layer to be captured. Then only I can able to get the flow physics near the boundary. And this is flow separations. So this regions, flow separation regions, you can able to capture it up, and also the recirculation. We can also call recirculation. These things I want to capture. I have to go with a fine mesh. Okay. And the next question, the ma'am asked the complexity involved. So the number of mesh count I have to use. Then I have to decide based on two things. One is computer memory and number of cells. Both are interrelated. I am using only laptop. Okay, I want to do the analysis. Then my laptop supports. My laptop is very small. The configuration very low. Then what will happen is I can't go with the more number of mesh cells. So I have to go with the 50 lakhs or 1 lakh mesh count. 50,000 or 1 lakh mesh count. Then only my laptop will support to run the analysis. Okay, but if you're using a huge server, then I can go with a bigger number of more number of mesh counts, so that because memory will be more. So more number of mesh count I can use, and I can able to solve the equations. So that's why. So where based on your available resources, okay, memory resource, computer resources, you have to decide the number of cells. Okay, that is one of the things. Okay, these are some of the meshing packages available. So Grid Pro, and then Grid Gen, ISM-CFD, and Gambit is absolute now. T-Grid and ANSYS itself in our workbench we can do the meshing. So these are the meshing packages available for us. Okay. Then once the meshing is done, now I have to give the boundary condition. So that's why I told in the beginning of these things. So I want to solve a flow inside a pipe. So first things I have to give the computation domain I have to create. Then I have to create the meshing I have to do. So when I do the meshing, so I'll put a coarse mesh and fine mesh near to coarse mesh and fine mesh. Depends on the requirement. I'm going to do that. So once this is done, then I have to use the boundary conditions. That is important. Then only we can able to solve. For example, here the flow is coming here. I have to give some boundary condition in this case. Here flow is going out. I have to give some boundary condition here. This is a wall. So I have to give some boundary condition here. So these type of boundary conditions we have to give in doing the analysis. Otherwise the flow cannot be analyzed. So for that we have different boundary conditions. One is inlet boundary conditions where we can define the mass flow. I know the mass flow rate. I can define the mass flow rate. If I know the velocity, I can give the velocity. If I know the pressure, then I can give the pressure inlet. Okay, like that I can define at the inlet. So which type of boundary conditions I am going to model it up. So that is the one part we have to tell. Okay, inlet boundary conditions. Then comes out to the far stream boundary condition. Okay, far stream boundary condition means, for example, this is my some of the aeroplane we have. Okay, I want to do this analysis of that. Then I have to do some outside domains I have to consider. Okay, this is geometry. This is geometry. Okay, whereas this entire thing is the computational domain. Now I have to use a far stream boundary conditions so that the flow will from the open atmosphere the flow will come in. So that is called as that boundary condition is called as a far stream boundary condition. Okay, so how long this how far this is far stream is from geometry means the flow physics should not affect, because this the flow behavior whatever you're doing, it should not touch the this surface. Okay, if it is not touching and it is going normally, then we can accept it, otherwise we can't do this analysis. Okay, so that is called far stream boundary conditions. Then we have on the wall, these are the walls. So wall we have to give a no slip boundary conditions. Okay, and where the velocity will be 0 and temperature will be 0, like that we'll consider, and then we'll work out no slip boundary condition. And then symmetry boundary condition. Symmetry means, now for example, if this model, if I divide into 2, then this left hand side will be equal to the right hand side. So I need only to go for solving the entire model. I can go with the half model. Okay, then the flow physics whatever we can rotate it up, and then we can solve it. Okay, so instead of doing the entire model, I am dividing into two small half model. Because of that, the mesh count will come down. The time taken for running the simulation will bring down. Okay, that's why this symmetry boundary condition used. And in the exit, we use pressure outlet or outflow boundary conditions at the exit. Okay, so these are the typical boundary conditions used to solve the flow physics. Okay, right. And next one is the analyzing. So now I have set the case, pre-processing, everything is set, ready. Then I have to analyze. So for doing the analysis, what I am going to do is I am going to solve the equations. So how long I have to solve? Some particular criteria should match. That is called the convergence criteria. That convergence criteria match, then I can stop the simulation. Okay, till that we have to run the simulation. So that is important. So the equations you have to solve. Okay, how many equations solve? It depends on the flow physics involved, everything. Then once the equation is how many iterations I have to run, it depends on the convergence. If the convergence is achieved, that is flow physics. For example, exponent value and numeric value matches, we can stop. Or particular type of threshold value if you give and it is matches, then we can stop. It all depends. So that convergence you have to reach, then we can stop the simulation and we can do the post processing. So how the accuracy is? So now we are saying CFD is good. We will replace experiments like that. We are saying, but how it is good? It depends on few things. One is the model you are using, the turbulence model. Okay, the model we are choosing and the discretization technique what you are using, and the grid resolution, whether it is a coarse grade or a fine grade, and how the boundary conditions are defined. All it matters. Okay, then based on that only we can able to tell whether I am able to do the CFD properly. Okay, right? So that is about the analysis. So once the analysis is done, then we have to go for a post-processing. So when you say post-processing, there are two things I told. One is visualization, another one is called as a reporting tool. So if you take the visualization, we can find out the overall flow pattern. And I want to see whether it is a high-speed flow, I can able to get the separation, flow separation, shocks involved, we can find out. And then some of the key features I told already, recirculation, you want to capture it, where the hotspot is there. These things I want to capture, then I can visualize using this tool and whether boundary conditions are proper or not. Sometimes we, instead of inlet boundary condition, we give outlet boundary conditions, and the outlet we give inlet. So entire flow physics will be altered. So to overcome this, we can able to check using the visualization tool. So these are the visualization tools available: grid plot, vector plot, contour plot, streamline plot, ISO plot, okay, XY plot, and animations. So these are the different plots available. With that, we can able to check it out whether this, for example, I am doing the grid outside in another machine software or a machine software. So when I import it up, whether all the features are available or not. Okay, all the mesh count mesh are properly imported. We have to check. If it is not there, then solving will be very difficult. So that is a physical check. First, we have to do that. Then second one is the vector plot. So now I want to see whether there is recirculation happening. So you can see here recirculation is happening. Okay, here also recirculation. We can see that how the flow behaves on the behaves. That we can find out using vector plot. and I want to see the counter plot where the high temperature is, where the low temperature is. I can clip it. So with that, I can able to get the values. Okay, that is about the counter plot. And fourth one is streamline plots. So flow over the flat plate or flow over the car or aeroplane. We can able to get the streamlines. Okay, that and path lines. That is a CFD useful. Isosurface means I want to clip the values to somewhere value. For example, I want to plot a temperature, then particular place I put temperature as 1000. So wherever 1000 is there, by using the isosurface, I can find out wherever 1000 is there. Okay, that way we can able to identify the error. Okay, and then XY plots, sometimes 2D plots, I want to put it up so that people understand. Then I can use this type of 2D plots. And sometimes people will believe only when they see properly in the eye. So for example, you can see here the flow comes over the nozzle. So how it look like, if they're able to see it up, then they will understand, oh, this is how the flow behaves. Then based on that, they can redesign or alter or modify or keep it accordingly. Okay, so these are how the visualization tools are working. And the next is the reporting tools. So when you say reporting tools, it will give a quantity values, whereas in the previous case, visualization tools, that will give qualitative results, whereas in numerical reporting tools will give the answers, quantitative answer. For example, I want to find out the mass balance, I want to find out the how much velocity is going out, I want to find out the temperature at different locations. So all these things is possible using this type of reporting tools. Okay, values we can get it up, single value we can get it up. Right. So these are the different packages. For post processing, n number of packages are available. So most predominantly people are using is the CFD post, and then this field view, okay, tech plot, and then CFX, okay. But these are all integrated. CFX, ANSYS, Fluent are integrated in ANSYS CFD post. There we can do the post processing. Okay, so coming to the last point is the case study. So whatever we discussed so far, if I implement in a real system, in the practical simulations, case, how it look like, what are the steps involved. So this one I took from my colleague, Dr. Venugopal's student, Pradeep. I'm also the DC member for him. So his study is investigation of electric vehicle battery cooling system using different phase change materials. Okay. So he has done different phase 1, phase 2 like that. I think 6 phases he had done. But for this explaining purpose, I used I took one phase from this. Okay. So this is a lithium-ion battery. Okay. So battery is mainly used to transfer chemical energy into chemical energy into electrical energy, or we can say electricity. So here there are two things. One is anode. So anode is the carbon, and this cathode. Cathode is lithium metal oxide. And the separator, we have in between we have electrolyte, lithium salt, dissolved in organic element. Okay, this is how the battery is looking like. Lithium element battery is working like this. Okay. Now the lithium ion battery, how the thermal management will behave. So usually the performance of the cell depends on both temperature and operating voltage. If both are having an issue, then you will not get proper result. Sometimes it will happen. So now if you see here, the operating range, the whatever in the first cell. So in one of the cells, so in one of the cells, the problem happened. So this is spread across the remaining cells. Okay, and then release a large amount of heat and flames. So this cannot be possible. Okay, so what is the necessity of thermal management? So I want to control the battery temperature within certain temperature variation or temperature limit to overcome the thermal issues and also to improve the performance values. Then I have to do some thermal analysis. Okay, that is why the CFD analysis comes into picture. Okay, now this is some of the battery output versus temperature, and this is cycle time versus the operating temperature. Now these are the different cooling strategies. Cooling strategies are available. So one is called as water cooling. Okay, one is called as water cooling. The second one is the air cooling, and third one is PCM cooling. Okay, so people use the natural convection method. Okay, so water can be go inside, and then it goes inside, and it goes. It goes inside and then comes out. Okay, so if you see the number of cells, almost 18,650 cells they have put it up. Okay, to analyze this result. Okay, so this is the cold flow Gaussian, and this also cold flow Gaussian, and remaining places the hot air may go in. Okay, and second one is the air cooling method. Okay, so directly air can be used so to cool the elements, and third one is the PCM material. So PCM material, different types of phase change material will be used so with a certain ratio, and this problem can be addressed. Okay, so now out of three, we are going to discuss about the PCM cooling. So what is the phase change material? So what it will do, it's a substance which releases or absorbs the energy at a phase transition, okay, from liquid to gas or gas to liquid. Then purpose is to provide the uniform or heat and cooling. Okay, that is a phase change material. So why this method, why they chosen this topic is, these are the research gaps they identified. So one is mainly the understanding of thermal behavior, transitional behavior, unsteady behavior of PCM. Okay, within the boundary cell is not investigated. That is the main reason they told. Then the temperature distribution, the unsteady temperature distribution from the distribution rate, okay, are lower, okay, are not matching. Okay, and third one is the different combination of PCMs for improving the regeneration to be investigated. So 50% to 50 is to 50 or 60 is 40. Like that thing is missing. And the fourth one is the cooling methods, passive cooling or active cooling. So vehicle running at a different speed encounter some environmental conditions. So how to mitigate it up. So these are the research gap the student, the scholar identified. So based on that, he come up with what are the problems we identified that he listed out. So one is still facing some considerable challenges within the primary difficulty coming from achieving the optimum battery performance, and then controlling the bad temperature is difficult, and bad temperature should become within temperature limit to avoid the thermal issues. So these things are the some problem definition. With that in keeping in mind, okay, they develop the objectives. So develop a PCM-based passive thermal management system for lithium-ion battery using for EV vehicle, electric vehicle. And then analyze the different system, different operating conditions called that is considering the environmental condition also. Okay, and third one is to analyze and compare the developed battery thermal management systems without conventional air cooling also. Okay, and last method is to model and simulate the development system in order to understand the behavior, effort, temperature variation across cells. Once the model is ready, we deploy it even in a real we sold it also. We go with that. Again, we will check for any discrepancies there or any improvement is possible. That things engineers will do. Okay, that is the main objectives of this problem. So this is how the simulation and experimental are going done. So combination of PCMs that meet the requirements were identified and studied experimentally. And CFD analysis consists of the two phases we are going to, two studies we are going to. One is 50-50 yeast, another one is there is paraffin wax and OM335. We are mixing it up. So these two we are mixing in 50-50, another one is 60 fluid paraffin wax and OM35 is 40%. Okay, then analyzing these two in different range of temperature, and then we will tell that which one is the better one. Okay, that will be implemented by our people. So we are done experimental. We are going to either validate whether it's numerical we are going with or not. Okay, so material properties. These two are the material properties: melting temperature and at the same time they give acetate solid. So with that you can able to get the required temperature. So these are the simulation boundary conditions or initial conditions. We can say 2D simulations, pressure based, and then it uses physics model as solidification with modeling method melting. I previously told about the turbulence model. So now we have this one is physical model involves solidification and melting. So here we are involving we are going to enable or not energy, transient, and gravity. So these are physically available models inside this compressive flow. So if we solve this flow physics of energy, then I can insert, otherwise not required. So boundary conditions, different boundary conditions. One is the pressure and one is the volumetric heat source. This has to be given as an input to this model. So these are the different experimental setup ways how this thermocouples are connected and how this PCM material will behave. So these things they physically captured here in our campus and then model it up. Okay, so this is a comparison of temperature between the simulation and experimental results. So the dotted lines, dotted points are shows the discrete phase. So it means experimental we can't take continuously in experiment. So this is experimental one. Another one is the CFD simulation line. So because we can take any number of location, any number of times we can take the readings. So that's why it is advantage. So if you map it up, so almost the same trend, it is following it up, and it's able to say we can go with this. And some of the experiment we had done with the chamber, climate chamber, we heated up inside, and then we done the experiment, same thing repeated in the CFD simulations, and we are able to capture it up for ambient at minus 20 centigrade. But even whatever design with, if you do it up, it properly matches with the experiment result. Okay. So they was also done for a cyclic loading. Cyclic loading means it's melting, freezing of PM, PCM, on-off heating conditions. Okay, all these things they have done it in one shot, and they find out the behavior of this thing. Okay. So what's the conclusion of this results? So the two PCMs are good, after which the 50-50 ratio gives the battery operating temperature is within the maintain this battery temperature at particular value. And then combination with different melting points can provide with 50 degree peak of temperature limit. And also the cyclic loading, 50-50 is good, numerically without shared good agreement. So CFD simulation shows good agreement between the simulator and experimental, so that you can see that the trend, whatever we are seeing, it is almost matching with the experimental. Okay. So what are the industry tools and research trends people are going with up? Industry tools is ANSYS, Fluent, COMSOL physics, OpenFOAM people are using to analyze this. And then AI and ML integration for predictive modeling, and also digital twins for energy storage and future direction. People are start to use digital twin. And research trends, optimization of storage systems, and safety studies or safety features can be considered under studies. So this is how the software and trends are working. And in conclusion, I can say CFD is a very powerful tool in energy storage system design. Okay, so it's not only for academic purpose, CFD used for industry purpose. Getting people for doing the CFD is very, very rare. So very difficult to get people in industries to get the CFD, to run the CFD analysis. And also it enhances the performance, safety, and cost effectiveness. There is advantage of CFD. And there is a possible challenges. There is opportunities in hybrid storage, hydrogen, and AI integration are possible with the CFD. So with this, winding up. So thank you for patient listening. So if you have any questions, I am ready to answer now. Thank you.
Participants, you can unmute your mic and ask your questions. Otherwise, you can put your doubts in the chat box. Participants, you can ask.
Any queries?
Sir, we know CFD has applications across multiple domains of energy storage. That is like thermal, that is molten salts and PCMs. In electrochemical, like lithium ion and flow batteries. In mechanical, compressed air and pumped hydro storage systems. Each of these has unique challenges and modeling requirements. Based on your research and industry perspective, which of these domains currently benefits to the most from CFD in terms of practical impact and innovation, and what are the key reasons behind that? Additionally, how do you see this trend evolving in the near future as energy storage technologies mature?
Yeah. Each one having its own advantage merits, ma'am. So if you take mechanical, that is going separately. So that separate teams are working. Electrochemical also. Battery means the battery, some research going on with battery. Because now, so lithium ion battery is, the problem is the recycling. So that is one of the problem. So people are trying with the different types of battery. There we need to optimize the fuel passages, the line. So there the CFD plays a major role, and even our faculty members put to file a patent. We are waiting for it has to be granted. So there is large potential to sell it up also as commercialization also possible. So that is the main thing. Now I am seeing the trend is in renewable energy only. So whatever people are using, that is focused mainly on the renewable energy. So that is one of the national mission also. So renewable energy resources. There, people are coming with the alternate solution for the mainly on the ICE engines. So for that, people are using battery, but battery, the problem is one is the costly, and also the recycling is an issue. And people are trying with fuel cells and hydrogen storage. So already in abroad, the hydrogen they started putting in the vehicles, and still we are trying it up. And the other one is the super capacitors that also people are working it up. Okay, so uh, every domain CFD plays a role. Okay, so energy technology. So that's why we are saying four domains. Four domains also equal importance are given, and people are working it up. Okay, so the impact definitely it will be huge impact because it's difficult to do the experiments, man. So experiments, if you do prototyping itself, it will take more cost. Okay, then we can't do it up in one prototype. So if you, even a small change, if you do again, you have to make it up. But in CFD, there is an advantage. You can n number of designs, you can make it, and then you can do the testing. Then finally, we can say one or two we can down select, and that can be experimentally proven it.
Sir, you have mentioned digital twins.
Yeah,
Do you foresee digital twins of energy storage systems powered by CFD
yeah, it will
becoming
come.
standard tools for grid operators and
Yeah,
industries?
definitely will come, ma'am. Now AI people are started using it. Even this last for semester for my students project I gave AI for the turbo machine applications. So they can come up with the values, whatever values they are able to do with the AI prediction. That is trend is matching with the experimental values. So that way we can minimize the number of CFD run also. So even CFD run also it's costly. So if you take 2 days, 3 days simulations. So if you number five simulations, and with this data, if you're able to use AI tools, then we can find out how the trend will be for different types of parameters. So with that, we can reduce the number of experiments, and the accuracy will be more.
Sir, for young researchers working in this domain, what are the most promising areas in CFD applications for energy storage to focus on in the next 5 to 10 years?
Definitely, it should be electrochemical battery-related operations. So even funding, they gave funding for hydrogen storage. Now the people, government is giving funding for almost 200 crores they spent on it for hydrogen storage. Okay, so there is a ANRF thing. Anusantan is going to invest more on this hydrogen storage.
DST, like
Yeah,
some
and it's a
funding
service
agency.
converted into ANRF. Then from the ANRF, we'll get a good funding.
Okay, okay, sir. Most of your students are doing in this domain, sir?
Not my student. Now I'm not taking students because of the heavy workload of sponsored research. So my colleagues are working on this type of areas.
Okay, okay, okay. Simulations also very easy only using AI tool like that.
Yeah, they have to learn AI tools. Okay, if you know that AI tools, then it can be done easily. Okay, so AI is the only thing. How to the connection between CFD and how to transfer data directly from CFD to AI, they have to understand. So my alumni students are working in industry. They said they are working on this AI in the industry to use this reduce the number of CFD runs. They are using it up in US. My student is working in US. So he said he is using AI tools. So based on that only I asked my student to try
Okay.
using the support. Yeah.
How do you see CFT contributing to India's energy transition goals, especially with the push toward large scale renewable uh, integration?
Yeah, that's why, ma'am. So see, CFD we use only systems. System is fine enough. So and if your manpower is there, then we can able to get the result easily. Okay, that's an advantage. So that is the reason it's interconnected with the CFD and experimental. So now even I got funding from ARDB for CFD. They gave two system, computer system, and one manpower to do analysis of shock wave in high speed flows.
Okay.
Okay, that way it will be definitely it will be possible. Okay, a lot of contribution can be done using CFD. Okay, with advanced tools. I can say AI with advanced tools. use, definitely it will be another 10 years we can able to do that.
Okay, sir.
I think on behalf of participants, you asked a lot of questions. You have gone through the slides, I think. Okay, thank you.
Participants, you can post your doubts in the chat box also. If you raise your hand, you will be given mic. In nitrogen storage system also, it is so much used, I think.
Yeah.
Safety. Okay. Thank you, Shivkumar sir.
Thank you.
You have, with your busy schedule, you came here for me. It's very happy. I'm very happy, and thank you so much.
Okay. Thank you, ma'am. Thanks for giving the opportunity.
Anisha ma'am, can you
Yes, ma'am.
conclude?
A very good afternoon to everyone. As we come to the close of this session 11, it is my privilege to express our heartfelt gratitude to Dr. Shivakumar R., Dean sponsored Research and Industrial Consultancy in BIT Chennai, for delivering such a thought-provoking and engaging lecture on applications of CFD in energy storage techniques. Sir, your insights into how computational methods can revolutionize energy storage systems have been truly enriching all of us. Once again, I thank you, sir.
Thank you, ma'am. Thank you.
Participant, could you please turn on your video?
Let us to have a photo session, please. Please turn on your video. Shivakumar sir, you also turn on your video. Shivakumar sir?
Yeah, I turned on, ma'am.
Ah.
Thank you.
Thank you, Badran sir.
Thank you.